In this video, we discuss solving trig equations using factoring. We will jump right in with 5 examples. First, solve cosine squared x plus cosine x minus 2 equals 0. The given equation is a quadratic in cosine x. Factoring was the first technique we learned for solving quadratic equations, so let's try to factor in this case. The expression factors as cosine x plus 2 times cosine x minus 1. Now we have a product equaling 0. So one of the factors must be 0. Now we are back to linear equations in cosine x that we know how to solve. We get that cosine x equals minus 2 or cosine x equals 1. The first equation has no solution since the range of the cosine function is the closed interval from -1 to 1. The second equation has solutions at the even multiples of pi. Therefore, the solution to the given equation are the integer multiples of 2 pi or the even multiples of pi. Next, let's solve the equation 2 sine squared x minus 3 sine x plus 1 equals 0. This time we have a quadratic in sine x. Perhaps we can factor as in the previous example. Factoring is a little harder when the leading coefficient is at 1, but this quadratic expression does factor as 2 sine x minus 1 times sine x minus 1. Since we now have a product equaling 0, we know that one of the factors must equal 0. And then we have linear equations in sine x to solve. We get that sine x equals a half or sine x equals 1. The solutions are x equal pi over 6 plus even multiples of pi in the first quadrant, x equals 5 pi over 6 plus even multiples of pi in the second quadrant, and x equal pi halves plus even multiples of pi on the vertical axis when thinking in terms of the unit circle. Now let's consider some examples involving more than one trig function. Let's solve the equation 3 tangent squared x minus secant squared x minus 5 equals 0. The equation has quadratic terms in both tangent and secant. When we had quadratic equations in only one trig function, we were able to factor the quadratic. Let's use one of the forms of the Pythagorean identity and substitute secant squared x equals tangent squared x plus 1. To simplify, we can distribute the minus sign and collect like terms. Now we can solve for tangent x. Since 2 tangent squared x minus 6 isn't a difference of squares, factoring isn't the easiest route to follow. We can add 6 and divide by 2 on both sides of the equation, and then we need to take the square root of both sides to get that tangent x equals plus or minus root 3. This can be written as 2 separate equations for convenience. From the unit circle, we know that tangent of pi over 3 is root 3, and tangent of 2 pi over 3 is root 3. We want all solutions, so we get that x equals pi over 3 plus integer multiples of pi, or x equals 2 pi over 3 plus integer multiples of pi. Next, let's solve the equation cosine theta plus 2 times secant theta equals -3. We note that theta cannot equal any odd multiples of pi over 2, since that is where the cosine function equals 0 and the secant function is undefined. If we get any of these values as solutions, we will exclude them as extraneous. Since secant theta equal 1 over cosine theta, we can multiply both sides of the equation by cosine theta to clear the fractions. When we distribute cosine theta on the left-hand side, we see a quadratic expression in cosine theta. We can add 3 cosine thetas to both sides and hope to be able to factor. The quadratic does factor into cosine theta plus 2 times cosine theta plus 1, and we now have a product equaling 0. So one of the factors must equal 0. And we get that either cosine theta is negative 2 or cosine theta is negative 1. The first is impossible, and the second occurs when theta equals pi plus integer multiples of 2 pi. We can factor out pi, and the solution consists of all odd multiples of pi. For our last example, let's consider an equation in which the solutions are not special value angles. Let's solve the equation 15 sine squared x minus 26 sine x plus 8 equals 0 for x in the interval from 0 to 2 pi. This quadratic expression factors as 5 sine x minus 2 times 3 sine x minus 4. Thus we have a product equaling 0. Therefore, one of the factors must equal 0. So we get that sine x equals 2 over 5, or sine x equals 4/3. Since the range of the sine function is from -1 to 1, the second of these has no solutions. We can use a calculator in radian mode to find the first quadrant angle whose sine is 2/5. There is another solution in the second quadrant. We use the reference angle found from the first quadrant to find the second quadrant solution. Therefore, the only solutions in the interval from 0 to 2 pi can be approximated by x equals approximately 0.415 or 2.730. This last problem was quite a doozy. As always, the process gets easier with practice. There's a lot of subtle stuff going on in these problems. In the next video, we will consider equations in which the trigonometric functions have multiple angle inputs.